let us start this lecture with a thought process. Education is not the filling of a pail, but the lighting of a fire. Pail is basically container, right, or something. It is not a content delivery and whatever we are doing, but that is not, but it is lighting of a fire which is lying within a person. So, in the last lecture basically we looked at the effect of the pressure on the laminar burning velocity, right, and of course, if you look at, we looked at that depends on the order of reaction, right. The pressure effect will be governed by the order of reactions. But however, let us look at some of the experimental data which is taken from the literature, like this is plotted here, and these are the burning velocity, pressure, atmosphere. You can see that most of the data are scattered around, and if we take curve, it comes around to be ACP minus 0.5. Keep in mind that this is meant for stoichiometric methane air. Temperature, the unburned temperature varies from 16 to 20 degrees Celsius, because they will be conducting experiment in various environment. So, therefore, it will be changing, and this is in the western country, so it is a low temperature. So, this is what it indicates. It indicates that burning velocity decreases with change in the pressure, right. And in some situation you may find that it is remaining constant, right, and some situation it may also increase, right, but that is not the we are discussing about it, but it can happen depending on the range of burning velocity, or rather it will be dependent on the order of the reactions, because we have seen that SL we have seen is proportional to P n by 2 divided by 2, n is the order of chemical reactions. Of course, in our analysis we have taken that as a single step chemistry, but in the multi steps chemistry, where which will mimic the actual situation, order can be depend on this is each individual reaction, but however if you look at a global sense, it will be varying from fuel air system to other, and also depend on the pressure.
So this equation and graph will be only valid for methane air?
It is valid only for stoichiometric methane air, and also the range in which it is being done. It won't be valid for all other things, right. So, therefore, this is a very important point. It is known as semi-empirical relationship, because it is not generalized, it is not from theory, right, it is from experiment. And people have also looked at the various data and couch in some other form, which we will be discussing just now. And before that, what I am thinking, we look at the effect of initial temperature on the burning velocity. If you look at the burning velocity, basically SL is proportional to, I have seen, P n minus 2 divided by 2, right. And if you look at the P is basically you can see that is temperature, right, is proportional to the temperature. P is, if I take ideal gas equation, P is equal to rho R U T, and of course then you can think of using basically right, it will be no, I think so if you look at SL, SL is proportional to basically alpha, right, by rho u, and rho u and also the fractions, right, average, and this is proportional to basically if you look at 1 over rho u, and from the reaction rate, because we know the reaction rate is proportional to basically rho n 1 plus n 2, and I can say n is equal to n 1 plus n 2. So, I can say that rho is equal to n, right, and this is basically n by 2. This is half, it will be okay, rho u square, right, this is half, this is also will be half, right, because it is a square. If you look at SL is equal to basically 32 by 9 alpha by rho u nu plus 1 m dot triple dash f, right, isn't it? So, therefore, if you look at alpha is kg by rho u Cp, and this is temperature average and this is temperature average, whereas average the Cp will be evaluated at average temperature and kg is evaluated at average temperature, and this I have, as I told, this is proportional to n, and therefore, SL you can say this is proportional to that, therefore, this will be proportional to n by 2 minus 1, right. So, you can say that rho P is equal to rho R T, right, and of course, this is basically if you look at molecular weight, universal gas constant molecular weight, and I can say that rho is basically inversely proportional to T. So, therefore, I can write down SL is basically inversely proportional to T, proportional to 2 minus n divided by 2. Minus basically you will take minus of this what you call minus of this. So, that is nothing but 1 minus n by 2, then 2 n by. So, of course, that depends upon order of reaction, but however, it is proportional to T power to the m, right, I can say, and that is being shown here. Burning velocity for stoichiometric methane air, pressure is 1 atmosphere, pressure is remaining constant. So, you can see these are the data, experimental data, and this is of course numerical data, which is matching well, except these are I think little higher values, which may be not the right one for the experimental that conducted by Andrews and Bradley. So, but however, this thing happens to be quite higher values, right, 1.5 to 2 times, and which is not matching with the simplified theory what we have looked at, because n the order of reaction, if you look at order of reaction, generally it will be maybe second order or the first order in between, right, kind of thing. So, then it will be very small values, m will be very small, but m is quite big here. So, that is the limitation of the present model what we are doing, but however, we will have to go by the experimental data, right, which is the right one kind of things. So, now what is being done, people have looked at experimental data and arrived at basically a semi empirical relation, which will be taking care the effect of the initial temperature and initial pressure on the burning velocity. So, there are several data which will be available in literature, but we will be looking at a very simplified version of burning velocity laminar correlation given by the Megalchi and Keck, right. This is the relationship, I am just writing directly, but it is a semi empirical relationship. Laminar burning velocity is equal to SL R. This is the reference burning velocities. Tu divided by Tu R power to the gamma and P by PR power to the beta power, and of course, there might be some dilution effect, right. Why dilution? Means there will be some recirculation of the product gases or nitrogen being diluted and other thing. The burning velocity will be affected by that. We will see little later on this effect. So, if you look at this SLR is basically can be given as Bm plus B2 phi by phi m, right, square, and this Bm different values is given here. For methanol, this is 36.9 to 1.1, and this B2 is 140.51 centimeter per second, and this phi is basically equivalence ratio, right, and phi m is your this constant, right, which is corresponding to the reference kind like constant values phi m, right, which will be taken from this, and this is laminar burning velocity at a reference condition. What is the reference condition? Reference condition is basically if you look at reference condition in this data, generally it is being taken also otherwise. UR is 298 Kelvin and PUR is taken as 1 atmospheric pressure, right, that is being taken. So, if you look at this gamma is also a relationship, that is gamma is 2.18 minus 0.8 phi minus 1, and beta is minus 0.16 plus 0.22 phi minus 1, right. This coefficient has to be taken because these are all empirical constant. Keep in mind that you will have to use proper unit. For example, Bm centimeter per second, B2 centimeter second. Naturally, what will happen to SLR? SLR also will be centimeter per second. Similarly, SL also will be centimeter per second. That means the unit has to be left hand side should be same as the right hand side, and these are of course, if you look at these are the same unit like you are using Kelvin. So, it will be non-dimensional. P by PR is atmospheric, that also will take care. So, this non-dimensional, and Y DIL is basically mass fraction of diluent present in fuel air mixture basically to take account of recirculation of product gases or diluent addition, right. Suppose for example, I am trying to extinguish a flame and look at what is the burning velocity, how it is decreasing, then naturally you will have to look at that way. So, you might be aware that in the gas turbine engines and other things there will be lot of recirculation of product will be taking place. Similarly, in the internal combustion engine, and recirculation is being used today as a methodology of decreasing the emission level, right, particularly NOx and other things. So, therefore, there might be some use in application also. So, this is the thing. What we will be doing now, we will take an example and see how we can calculate using this data.
So what do you mean by diluent?
Diluent means, suppose for example, product gases. Product gases means it will be carbon dioxide, maybe if it is unburnt little hydrocarbon, right, and also the like nitrogens and other things. Diluent generally it will dilute the mixtures, right, and inert gases being used, and also the sometimes the combustion product is being also recirculated, right. There will be advantage of using that. One is that heat which is going out can be recirculated, so the temperature can increase, inlet some mixture, but it is having also bad effect, like carbon dioxide is there, it will act as a diluent. So, Cp value will be affecting the temperature, the temperature which will be getting. So, and as a result, if you want to reduce the NOx, generally the thermal NOx which is predominant, so reduce the NOx, but you will have to pay penalty of reduction in the power level, right. And for example, I want to extinguish a flame, what I will do? I will have to add something which will take the heat out. We will be discussing that little later on. So, therefore, these are being used, right, as a diluent. So, we will take an example, let us say that determine laminar burning velocity SL of propane air mixture with phi is equal to 1.2 for A, we will be doing at T is equal to 298 Kelvin and pressure is equal to 1 atmospheric pressure, right. And B will be looking at T is equal to 800 Kelvin and P is equal to 1 atmospheric pressure, and C will be looking at T is equal to 800 Kelvin and P is equal to 20 atmospheric pressure, right. So, if you look at first one is basically reference state, right, and second one there is a increase in temperature, right, 298 Kelvin to 800 Kelvin, and the third both the temperature and atmospheric pressure is being changing, right. So, let us look at the solution. We will be using the empirical relation of Keck and Megalchi. So, we will be using this empirical relationship, and for the first case what we will do, we will have to find out SL, basically reference, right, that is the reference temperature. So, that will be equal to Bm plus B2 phi minus phi m whole square. So, if you look at the data which we have shown in the last slide earlier, that Bm for propane, right, is 34.22 plus, maybe I will do one thing. This is basically, if you look at Bm for propane is 34.22, right. So, that I will get 34.22. Then what is B2? B2 is equal to 138.65, that is minus 138.65, and phi in this case it is 1.2, right, 1.2 minus phi m is 1.08, this will be whole square, and then if you look at that is SL R would be 32.22 centimeter per second, right. So, that is coming as 32.22 centimeter per second. Now, we will have to look at the at 800 Kelvin and what atmosphere pressure. Is it you are having some doubt? माइनस आया, ये माइनस इधर है ना ब्रैकेट में, इज नॉट विजिबल, दिस माइनस इज नॉट विजिबल. Okay. So, let us look at this one because we have seen that SL we will have to use now for the different pressure and temperature than the reference. So, we will have to use SLR SL is equal to SLR TU by TUR gamma and P by PR beta and 1 minus 2.1 YDL. Now, in this case what is given, the DL YDL is 0, right. In this case YDL is 0 and that P is equal to PR is equal to 1 atmosphere pressure. So, this will be 0, this will be 1. So, I am getting SLR TU by TUR gamma, right, and I need to evaluate the gamma, right. So, we can find out gamma is basically 2.18 minus 0.8, 1.2 minus 1 and that is coming around 2.02, right. So, then what I will do is basically SLR we know 32.22 into temperature is TU is 800 Kelvin and this is 298 Kelvin, right, and gamma is 2.02, you will get 236.8 centimeter per second. So, this is my value, that is SLR 800 Kelvin is basically 236.8 centimeter per second. This is my answer. So, let us look at C, that is corresponding to TU, right. This is TU is equal to 800 Kelvin and P is equal to 20 atmospheric pressure. So, we can find out SL. Basically for this we need to find out beta, right. Beta is basically minus 0.16 plus 0.22 phi minus 1. So, that will be if you substitute this phi is equal to 1.2, you will get minus 0.116. Right. So, the SL I can find out as SLR TU by TUR gamma P by PR beta because YDL is 0. So, therefore, I can get this is 32.22 into 800 by 298, gamma is 2.02, and this is 20 by 1, that is beta is minus 0.116. So, that happens to be basically 167.29 centimeter per second. So, you can see that if the pressure is being increased, the SL has been decreased as compared to the temperature effect. Why? Because the pressure is having negative effect. That means the burning velocity decreases with increase in pressure. So, that effect is being nullified with the increase in this example, right. So, that is the point you must appreciate out of this. And this is of course SL at 800 K and pressure of 20 atmospheric pressure. So, that is the thing I want to illustrate, that you can use a semi empirical relationship and then calculate for your design purposes and other things, but this is limitation, this is limited because of fact that this data has to be used very carefully, right. Wherever it is possible, you will have to know, or in other words, right, you will have to use this data within the range given by the experimental process, right. So that you will not go beyond the range for which this empirical relationship will be valid. I think stop over here and we will discuss the other thing in the next lecture. Okay, thank you very much.